You type a query and your vector database gives you back 10 most similar items out of a billion in about 5 milliseconds. Interestingly, your vector database does not look at all billion vectors, maybe just a few hundred, but still it manages to find the right answer almost every time. And that almost is the whole story. Let me tell you how. In this video, we'll discuss exact versus approximate nearest neighbor search, different algorithms in ANN and why HNSW is the default, intuition behind HNSW and how it works. Then we'll see how exactly your query travels within HNSW graph and how the search works. How does the HNSW graph gets built when you index the data? We will see three most important parameters: M, EF construction, and EF search. Trade-offs of choosing these parameters and how to correctly set them. At the end, we will see the code of how to define these parameters while creating an index inside vector database. Exact nearest neighbor search is refreshingly honest. You hand it a query, it looks at every single vector in your database and gives you top 10. It is true top 10. It is guaranteed to be correct because it has looked at every vector. Why not always use exact nearest neighbor search? Let's say you have 10,000 vectors. Instant search. 100,000, it's fine. A million at 768 dimension, it can take around 3 seconds and it scales linearly. As the number of vector grows, the time taken for search increases. This is the main problem. So we trade. ANN does not promise you true top 10, but it promises something very close and very fast and let you decide how close. So that trade needs a number and that number is recall. Exact nearest neighbor search gives you true top 10. It's your answer key. And ANN gives you its own 10. Let's say 9 results are matching, then your recall is 90%. In ANN, when we say the word approximate, it is not a polite way of saying wrong or incorrect. In semantic search, the difference between 9th and 10th result is usually invisible to humans. You are trading the rounding error for 1,000-fold speed up. And the thing which matters the most is you are measuring the recall. Never ship an ANN index which you haven't measured. That's the one rule. Now let's talk about different algorithms in ANN. Majorly, there are 4 families. Number 1, tree and space partitioning. It contains ANOI and KD trees. Then we have hashing, which has locality sensitive hashing. Third one is clustering or inverted file, which is inverted file and product quantization. Then we have graph based, which is disk ANN and HNSW. I will not go into the details of which, maybe in future videos. Let me know in the comments if you have a preference. But for now, on a very high level, if you have less than 100,000 vectors, then choose flat, which is also called exact brute force approach. If you have billions of vectors and memory is a constraint, then you can use IVF PQ or disk ANN. And if you have a static dataset and you can rebuild the index nightly and your RAM is low, then you can choose IVF or ANOI. And in the scenario where your data is changing constantly, you need high recall and RAM is available, then you choose HNSW. Now let's talk about HNSW. Forget vectors for a minute. Let's imagine a library with 10 million books and you want to find a book on graph neural network. One approach can be to start from first shelf and look at every spine and every book till you find your book. It works, but this is painfully slow. You'll have to maybe sleep in library for 2-3 days, depending upon how huge the library is. But that is not what you do in real life. You enter a library and you check for floor directory first. Let's say third floor is for science. You go to third floor, then you look at floor directory. Let's say IL12 is for computer science. Then you go to IL12 and you see a shelf labeled machine learning. In that shelf, you look at around 40 books and you get your book. That's what you do. And here is the part I want you to hold on to. None of those directories are books themselves. They just exist so that they can help you get close to what you're looking for. That's HNSW. That's the entire idea. Everything else is just the detail. What is HNSW? HNSW stands for Hierarchical Navigable Small World. Fancy name, but very simple concept. It organizes your data into layers. Top layer, extremely sparse, handful of nodes connected with very long connections, very long jumps. Medium layer, progressively denser, medium jumps. Lowest layer, which is also called layer 0, it contains every single vector. Nothing is missing. Here is the structural fact people miss. The layers are not different data. A node promoted to layer 3 also exists on layer 2, 1 and 0. It is the same vector present on multiple levels with different set of neighbors. Each layer is a strict subset of layer below it and layer 0 is the complete set. Now let's see how your query exactly travels within HNSW index and how the search works. For this section, I want you to assume that structure already exists. We'll create this structure in the next section, but for now, I want you to see how search works, because once you understand how search works, indexing is very similar. Let's trace one query end to end. But before that, there's one word, greedy. I'm not kidding. You will hear this word constantly in this space, and it means something very specific and very simple. A greedy search always takes the next best step. It doesn't plan ahead. It doesn't consider that a slightly worse step might lead somewhere better. It doesn't go back and reconsider. It is like walking down the hill in a fog. You can't see the bottom, so you look at the ground around your feet. Step in whatever direction goes down fastest and repeat. Simple, fast, and usually gets you to the bottom. Usually. Sometimes you end up in a small dip halfway down where every direction around you goes up, so you stop. Convince you have arrived at a lowest point, while the real valley floor is 100 meters away. That's called a local minimum, and it's the main way greedy search fails. Now coming back to HNSW search, it works in two phases. Phase 1, the descent. You start at a fixed entry point at top layer. The node is fixed. It is not the node which is closest to your vector. It is just a fixed launch pad. This also means starting a search does not cost you anything. No lookup, no scan, just jump right into it. On upper layers, search is very simple. Here is the entire procedure. You are standing on a node, measure the distance from your query to the node you are standing on. Now on this layer, look at its neighbors. Measure the distance from your query to each of those neighbors. Is any of them closer to the query than where you are standing? If yes, walk to the closest one and then repeat. When no neighbor is closer than the node you are standing on, then you're done with this layer. You can go one layer below. That's it. It's pure greedy walking, one node at a time. The important thing about upper layer is you only ever remember one node, nothing else. No candidate queue, no good result set, nothing. Just one node. That's all. Phase 2 of search, which happens at layer 0. And this is the real work. At layer 0, the behavior changes completely. And this is the part worth slowing down for. Why change at all? Because greedy walking is fast, but it is sloppy. It finds one good node and it can get stuck in that local minima, which we talked about. At the bottom layer, you need the genuine top 10, not one lucky hit. So you stop walking a single path and start exploring. And here is the setup. You have just arrived at layer 0 from the upper layer, standing on the same node. Let's say E, which is distance 50 from your query. The user wants two results. Top K is 2. And you have set EF search equal to 4, which means you will keep a running list of around 4 best nodes you find along the way. You maintain two lists throughout this search, the candidate queue and the result set. The candidate queue is every node you have heard about but haven't visited yet. It stays stored, so the nearest unvisited node is always at the front. That way you always explore the most promising lead next. And the next is the result set, your current best answer. It has fixed maximum size equal to EF search, 4 in this example. Whenever something better shows up and W is full, the worst entry gets kicked out. So the thing you always need to know about W is what's the worst thing currently in it. That's the bar. Right now candidate Q has just E in it, W is empty. Let's go. Step 1. Visit E. Pop E of the candidate queue. It's the only thing there. Look at E's neighbors on the layer 0. A is 30 away from query, B is 45, and C is 70 away. For each neighbor, you ask one question. Could it still improve your answer? A neighbor makes the cut if it is closer than W's current worst, or W is not full. A neighbor that makes the cut does two things at once. It goes into the candidate queue, a lead to visit later, and into W. W is still filling up, so all the three makes the cut and goes straight in. E itself also counts. It is a node we have seen. So now candidate queue is A30, B45, C70, and W is A30, B45, E50, and C70. 4 entries, it is full now. Step 2, visit A. A is the nearest thing in the candidate queue, distance 30. So we go there next. But first, let me tell you about the stopping check. Is A farther from the query than the worst thing in the W? W's worst is C at 70. Is 30 greater than 70? No. So it's worth continuing. So A's neighbors are D12, F35, and G60. D12 and F35 both beat W's worst, so they make the cut into the candidate queue and into W, kicking out the weakest entry. J60 is already farther than everything already in W, so it does not make the cut. We note we have seen it and move on. W is now D12, A30, F35, and B45. Notice W's worst tightened from 70 to 45. The bar just got harder to clear. Step 3. Visit D. D is nearest in the queue, 12. Stopping check is 12 is greater than 45. W's worst? No. Keep going. D's neighbors, H8, I20, J40. H and I beat W's worst, so they make the cut. J40 does not. Now the new W is H8, D12, I20, and A30. Bar tightened again. Worst is now 30. Step 4. Visit H. H is nearest. Is 8 greater than 30? No. H's neighbors are K9, L25, M55. K9 beats W's worst, which is 30. So it makes the cut. L25 and N55 don't. So now new W is H8, K9, D12, and I20. Bar is now 20. Step 5. Visit K. K is nearest. Is 9 greater than 20? No. K's neighbors are N22, O60. Neither beats W's worst, which is 20. So neither make the cut. Neither one even enters the queue. W unchanged. H8, K9, D12 and I20. Now step 6. Visit I. I is nearest remaining. Is 20 greater than 20? Equal. Not strictly worse. So we will still continue. I's neighbors right now are P45, Q50, neither beats 20, so neither makes the cut. W unchanged. Step 7, pop F and stop. F is the next in the queue, which is 35. Stopping check is 35 greater than 20? Yes, it is. So we stop. And here is why that is safe to stop. The candidate queue is sorted nearest first. So F was the single best remaining lead. If even your best remaining lead is worse than the worst thing already in your top 4, then nothing left in the queue can possibly improve your answer. Going on would be a wasted work. Finally, we return the results. W holds H8, K9, D12 and I20. The user asked for top K, which is 2. Take the best 2, which is H and K. Done. What just happened? 4 things to notice here. W tightened throughout the search. Its worst entry went from 70 to 45 to 30 to 20. That bar rising is the search converging, and it is what eventually triggers the stop. Second, you visited 7 nodes but saw about 20. Every neighbor that could still improve your answer goes into the candidate queue. Seeing a node is cheap, one distance calculation. Actually visiting it and expanding its neighbor is what costs time. Third, W never held more than 4 entries, but it drew from all 20 nodes seen. W is not any single node's neighbor list. It is a running best of across the entire journey, fed by every node you have passed through. EF search controls everything. Make it 8 instead of 4, the bar drops slower. The stop fires later. You visit more nodes, you find better answers, but the query takes longer. Make it 2 and you stop sooner. You visit lesser nodes. That single number is your speed versus accuracy dial, and you can change it with every search query without changing the index. Now let's talk about the 3 parameters you just met: M, EF search, and top K. M is the number of connections a node makes to its neighbors. And there's one more parameter here, which is M max. M max is the maximum number of connection a node can have. M max is generally equal to M on upper layers, but on layer 0, there is exception. On layer 0, M max is equal to 2M, twice as many connections as on any other layer. Why double connections at the bottom? Layer 0 is the only layer that holds every vector, and it's where the final fine-grained search happens. So it does the heavy lifting, and it needs to stay well connected to reach the true nearest neighbor. EF search is the maximum size of result set W. EF search should be greater than or equal to top K, because W cannot return more entries than it can hold. Third parameter is top K. How many results user asked for. How HNSW index gets built. If you already understand search, you mostly understand build as well. It's just at the end we do a little bit of wiring to the new vector. That's the only difference. When a new vector arrives, HNSW decides 2 things about the new vector. One is on which layer it will reside on. Second, who are going to be its neighbors. That is the whole job. Let's take them in order. Decision 1, deciding the layer. For each new vector coming in, HNSW decides randomly on which layer it will reside on. It is completely random and is decided by exponentially decaying probability formula. So let's say if m equal to 16, which is a typical real world value of m, then roughly 1 in 16 vectors will go to layer 1, 1 in 256 vectors will go to layer 2, and so on. Decision 2, finding the neighbors. This is just like search. Let's reuse the exact graph from the search section and drop in a new vector. Let's call it x. That lands right where our query was standing. Same spot, same distances. X is 8 away from H, 9 from K, 12 from D, 30 from A, 50 from E. Every number you already know. Using exponentially decaying probability formula, let's say x land on layer 0. The common case. That means x lives only on layer 0. So first it has to get down there. The descent is search, verbatim. Start at the entry point up top and greedy walk down. EF equal to 1. One node at a time, layer by layer, exactly as before. No connections are made on the way down. X is just navigating to its neighborhood. Nothing new to learn here. Now X reaches layer 0 and it will search on layer 0. Exactly as we just saw. Same candidate queue, same result set, exactly the same. The only renaming, the size of W is now controlled by EF construction instead of EF search. Set EF construction equal to 4 and the trace is identical to the one we just did. X ends up with same shortlist. W equal to H8, K9, D12 and I20. 4 nearest candidate. Now X has to choose which ones to actually connect to. Here we are keeping M equal to 2. Most important part, choosing the neighbors. And why nearest is a trap here. The obvious move, connect to the 2 closest, H8 and K9. Done. But we don't do that. Let's see why. H is 8 from X, K is 9 from X, but H and K are practically on top of each other. The distance between them is only about 4. They are in same direction. If X connects to both, the second link is almost wasted. Anywhere H can take you, K can take you too. Meanwhile, D is 12 from X, a little farther, but it is in a completely different direction. Its distance to H is about 15, farther than it is from X. D opens a door that H and K don't. That's exactly the test the paper selection heuristics apply. Walk the candidates nearest first and keep one only. If it's closer to X, then it is to every neighbor you have already kept. H8, first one in, nothing to compare against, let's keep it. Now the neighbor is H. Let's take K. Is K closer to X than to H? No, it is closer to H. K is redundant, we'll skip it. Same with D. Is D closer to X than to H? Yes, so we'll keep it. Now the neighbors are H and D, two neighbors, and we stop here. So X connect to H and D, not H and K. It deliberately passed over its second nearest node to grab a link that points somewhere new. Why to go through this hassle? Because a graph wired only to the nearest neighbor quietly falls apart into islands. Picture two tight clusters. If every node only links inside its own neighborhood, there is no bridge between them, and a search that starts in one can never reach the other. The heuristics forces those bridges. It keeps one long diverse link instead of two redundant short ones. That's what lets HNSW stay connected on clustered data and reach high recall. And it's the paper's headline contribution alongside the hierarchy itself. Next is trade-offs and how to actually set the parameters M, EF search, and EF construction. Before that, let me tell you about EF construction. M and EF search we have already discussed. EF construction is the parameter you set while you are building the index. It's a build time parameter. You cannot change it later. So based on the paper, choose EF construction in such a way that recall should be close to 1 while you are building the index. In real life, if recall is 0.95, it is good enough. Now let's put these three parameters together. As we have discussed before, never ship an ANN index without measuring it. And here is how. Pick M from your dimensionality and recall target. Default value is 16 and you can adjust from there. Regarding EF construction, it's a build time parameter. As we discussed, set EF construction in such a way that build time recall should land around 0.95 plus, measured against exact search on validation sample. It should not be guessed. To set EF search optimally at query time, you need to plot recall against latency, and you need to pick the knee of that curve. It is exactly the point where more EF search stops buying you meaningful recall, and it will start costing you more time. So if you are using Redis as a vector database, let's see how you can set these parameters. So we have M, EF construction, and EF runtime. So this EF runtime is actually EF search. So if we go here, we will see this ft.create command. Here you can put the index name, you're putting this command on hashes, you're defining the prefix, and inside schema, you are defining that it is an HNSW index. And at the end, you can define here M equal to 40 and EF construction equal to 250. And similarly, when you're writing the search command, you can pass this parameter EF runtime to set the EF search. This is how HNSW index works. I hope this video was helpful. Let's meet in the next one. Thank you so much.